In this tutorial, we'll look at different ways of visualizing hard and soft data graphically and see how to get high-quality raster and vector graphics out of Grasshopper. So for this one, we're picking up where we left off at the end of the last tutorial. You can also start from the 2.3 DataViz begin Grasshopper file in the source files. Just make sure when you're starting from this file that, first of all, you have the subway entrances Excel file loaded, which is going to be necessary to read in data from Excel before you can turn this on. We did this last tutorial, and in fact, I'll just run it now. As well as making sure that you have your Earth anchor point set. That's an important piece where we're going to set the sort of geographical coordinates of our rhino model so that it knows where to map all of the geometry. So with those things settled, what we'd like to do is color code our buildings based on their year data. So we've already up here retrieved the value at index 3, which is the construction year. And what we want to do is color code all of these parcels based on that data. So we're going to remap numerical values from a year range to a simple range from 0 to 1. So for that, we're going to use a component called remap, which is going to live under I think it's under, oh no, it lives under math, under domain, remap numbers. And we want to specify a source domain, which I'm going to type to be sort of the lower bound of the building age here. Let's say we'll do 1800 to, oh, and I have to put this in a panel, so I'm going to preface it with a quote mark, 1800 to 2017. You can also manually create a panel and just type this in. I'm just using a shortcut where if you type a panel, a quote mark when you double click and then type some data, it'll create a panel pre-populated with that data. So that's going to be our source range. And then these are going to be the values that we try to map. And this is going to scale all of those values from this range to the target domain, which is set by default to 0 to 1. So now we have a bunch of values between 0 and 1, which will be useful to us in a second when we try to turn them into colors. So to do that, we're going to grab the gradient component, and we're going to construct a little bit of a custom gradient. I'm going to use this guy, and I'm also going to add one more color. So I'm going to scooch these up a bit like this. And we can eyeball it and then adjust it later on. And then if I drag from over here down, I get one more color, which I'm going to right-click and make black. Because there are some parcels in our data set that don't have valid data, and that will probably come through as a 0 in our remap data values. So we want to make sure that within the reasonable range, stuff shows up with a color, but then something that's really low, like probably none of these buildings were built in year 0, then it should show up as black. So we're going to take these values and plug them into the T input. This also has a default range of 0 to 1, so you could modify the range here, or you can modify the range here. And I prefer to have manual control over the numerical remapping using a remap component, but it's up to you. And we want to use these colors that we've created, because if we look, what we're getting back, where we fed in a list of values, we're now getting a list of colors back. And we want to go to the Display tab and grab Custom Preview. And we're going to plug in these colors as the S input for shader. And we can see that this has a data structure from 0 to 09501, which is the same as the data structure of our boundary surfaces. So if I plug in my boundary surfaces, and we may need to deselect this and also probably hide the preview of the boundaries just so that we get a range. So the older buildings are in green, the newer ones are in red, and the ones for which there probably isn't any valid data are shown in black, which is exactly what we wanted. So we can also, there's another way to color geometry other than custom preview. You'll notice that as I orbit this, the colors of these change ever so slightly. It's like they're a little bit shiny. And we can reduce this by using mesh colors instead. So if I select this preview component and turn off preview, and instead use, and I'm just going to search for this, mesh colors, we can actually feed in the exact same inputs, this series of surfaces and this series of colors. It'll take a second because it actually has to calculate the mesh for each one of those surfaces. So we'll plug in our colors. And now we get a consistent matte color representation that doesn't change based on our orientation. So I actually find this is better for diagrams. The other nice thing about this is that we can use it on our meshes that we've already created down here, which, if you recall, are our 3D building representations. So right now I'm just coloring those 2D parcels, but if I plug in the meshes that I've already created to this component, then we'll see a nice 3D representation color-coded by building year. So how do we get a nice graphic of this? Now, you can always just take a screenshot using print screen or something like that, but there are better ways to get high-quality, high-resolution graphics out of Grasshopper. So actually, this applies to Rhino in general. So if you type with a hyphen first, this is a critical component, view capture to file, then it will ask you where you want to save the file. So we'll choose Browse, and I'm just going to put this on my desktop as capture example. I generally find that PNG captures do better than JPEGs, but it's your call. And you can set the scale multiplier to be something other than 1. So if we set this to 3, we're going to get an image that is scaled 3 times whatever our viewport width and height is, which is quite useful. So go ahead and do that. So that's one way to get a sort of very high-res capture out of our Rhino environment. And yeah, you can see it's very, very high-res, will look good printed or on screen. And there are also ways to get vector data out. This requires a little bit more work. So everything we're looking at here is just in the Grasshopper preview. We don't have anything in the Rhino document. But if we want to get something into, say, Illustrator, then we're going to have to create some objects in the Rhino environment that we can export. And for that, we're going to use a component from Human called create_hatch. So go ahead and under creation, grab create_hatch. And this component works almost exactly the same as the boundary surface component in that it'll take lists of curves and create hatches, but it will interpret interior curves in those lists as voids, which is exactly what we want. So we can take the data from this p-shift component prior to the boundary surface and plug it in as C, and this may take a second. And then in order to tell it what color we want to create for these hatches, because hatches are Rhino objects, we need to create attributes for these hatches. This is true for any sort of baking workflow using Human, is that you'll need to construct attributes yourself. So under creation, use create attributes. And we're going to use the colors that we set up as the color input of this create attributes component. And we could also specify a particular layer. So right now my layers are hidden, but if I wanted these to go on layer 01, I could type layer 01 into a panel and plug those in as the layer. And then it would cause these hatches to show up on that layer, which is quite useful. So I'm going to plug this ATT input in here. And then I'm going to create a boolean toggle, which I will set to true, and plug it into the B input for bake. So once that's done, we see it show up in the Rhino context. And these are now objects that we can select in Rhino. And we can also export them to Illustrator. So I recommend doing this from a top view, so we can just go to top, or you can type top in the command line. And I'm going to select all of these hatches and type the export command. And I'm going to say Illustrator export example, and be sure to choose Adobe Illustrator as the output format. I'm going to use snapshot of current view. I don't usually use a scale. I find it to be a little bit unpredictable where it shows up when you do this. And go ahead and click OK. And then I can fire up Illustrator, go ahead and open that file. And it's very small right now, but I will size it up. The nice thing about using hatches from the Rhino context into Illustrator is that they come in as sort of filled objects. So that's they're objects with fill but no stroke, and their color is preserved. Sorry, I'm struggling to get this to come in without scale. There we go. All right. There we go. So these objects now are very nice sort of vector graphic objects with an appropriate fill color and no stroke. So if you wanted, you could add like a black stroke to all of these for the purposes of a diagram or something like that. And that's a little hefty, so maybe we'll reduce the stroke weight. And now we have a really nice, clean, color-coded diagram that we can use for other purposes. So that's very good for sort of hard data where there's sort of a specific correlation from item to item. But what if we want to represent something that's more like a field condition, something that's a little more abstract? So we're going to need to, first of all, kind of invent that data or construct a sort of relative set of data. And for that, we're going to be using the data that we pulled in before. I'm going to turn on preview again just so we can see. And that was the points which we read in from Excel, which were the locations of the subway entrances. So what I want to do is create a sort of field representation of distance from those subway entrances. So what we want to do is create one point for each of our building footprints, and then we're going to measure the distance from that point to each one of our subway entrances. I'm just going to delete all of these hatches for now. And so in order to get a point for each parcel, remember that as the data came in, it was kind of already in point format from our feature points. So I'm going to go over here and use another p-shift, because remember our data is structured in such a way that it has 2 layers of hierarchy per feature and then per sub-feature, where for this we don't really care. We just want all the points for every feature. So when we plug in our feature points, that should do it. And then you can actually use the regular old average component from the Math tab under util average. And it will actually average points in addition to numbers. If we do preview off, what we are left with is a single point at the averaged location of the sort of vertices of these features. This is a sort of approximate way to grab a center point, but it works for our purposes. So now we've got 1 point per feature, and what we'd like to do is measure the distance from each one of those features to its closest subway entrance. So for that, we're going to use a component called closest point, which lives under vector point closest point. And we're going to use our feature points as p, and then the C input looks for a cloud of points from which to select the closest value. So for that, we're going to use these points that we've created here, our subway entrance points. So this will have now found the distance from each feature to its nearest subway entrance. And this is just an as crow flies distance. We could get more sophisticated if we wanted, but this is just as a demo. And what I want to do is something a little bit funny. I want to actually turn this into a 3-dimensional graph where I extrude up or move those points based on their height. So I've lost this here. I'm going to right-click and choose Zoom to recenter the viewport on all of the points that we've found. Let's try this again. Zoom. There we go. So I want to move these up in space. I'm also, just for speed's sake, I think I'm going to turn off preview of all of these other elements. So preview off. We can turn preview back on. So now we're just seeing these points and the closest points that they've found. So I'm going to use this distance with a z vector. So we're still in this vector tab, vector z, and we're going to use that with a move component. So under transform move, under Euclidean, we should be able to take this vector and move our average points up by their distance to the closest subway entrance. So what we've done here is move the points up based on their distance. So you can see where there's a subway entrance, they haven't moved very far. There's a low distance. And then where they've moved up in space, they're very far from the nearest subway entrance. So this creates sort of a surface that represents their kind of distance to the nearest subway. And we actually want to visualize that surface as a 3D thing for the moment. So we're going to use a component under mesh called Delaunay mesh. And Delaunay mesh will take a series of points and just construct a sort of neat set of triangles that pass through all of them. But in order to use this full set, we're going to flatten the data coming out of here to create a single list. And then when we plug this in, it's going to create this mesh that passes through all of it. So that's already looking much better. And we could visualize something like this as sort of a 3D graph of the distances from subway, but I think it's maybe more useful to see it in a 2D form. So you're probably already familiar with the idea of using a contour map as a way of translating a 3D topography into a two-dimensional drawing, and that's exactly what we're going to do. So I'm going to turn off preview for all of these. And I'm going to grab the contour component, which I believe lives under intersect, mathematical contour. And we're going to supply this mesh that we just created a base point, which is just going to be 0, 0, 0. I'm just double-clicking and typing 0, 0, 0 for that and hitting enter. And then we need to specify the distance between contours. And for that, I'm going to also double-click and type 100, which is just going to be 100 feet. And now we get a contour map that's cutting through that virtual surface. But if we look at it from a top view, which I'm getting to by just typing top, we see a sort of cool contour representation of distance from the nearest subway station. Now, contours can be ambiguous. It's not clear what's higher and what's lower. So we may want to do one additional thing in order to color code these to make it clear what's sort of a low contour versus a high contour. So for that, we're going to grab a single point from each contour, which we're going to do with just the curve ends component. So under curve analysis endpoints. And this will give us 1 point per contour. We don't actually care where on the contour it is. We just need its elevation. And we're going to deconstruct that point using vector point deconstruct. So now we can extract just the z elevation of each one of those contours. And then we're going to use a remap values component. We saw this earlier under maths domain remap numbers. Plug in z, set our source domain, and I'm just going to use 0 to 2000 as sort of a distance range that we want to map from. So I'll create a panel, 0 to 2000. And set that as the source domain. And we can either use color or line weight to represent this, or maybe even both. Why don't we try both? So for line weight, we're going to go to the Human tab and go to Display and choose Custom Preview Line Weights. Grab our contour curves and supply the value from remap in as the thickness or the line weight of these curves. Now, by default, these values are all coming in 0 to 1. Remember, the default target domain of remap is 0 to 1, so we need to construct one. So what we can do is go back to the maths or sets tab. Actually, it is the maths tab and domain, construct domain, and create a couple sliders. I'm going to do one at 2 and one at 5, let's say. And I'm just doing that by double-clicking and typing a number to quickly create a slider. And we'll plug that in as the default domain. And now you'll see that when I reduce this value, the line weight of these contours is changing. So I can see that there's a low line weight wherever the distance to the nearest subway stop is very low, and a thick line weight for those areas that are sort of further from the nearest subway entrance. I'm also going to turn off preview and all these other things just so we have a clean diagram. So this is already much better, but we can also manipulate the color, which we'll do in a similar manner. We're going to actually copy this remap component, but this time we're going to disconnect it from this domain by right-clicking and choosing Disconnect Domain. And then, just like before, we're going to use a gradient. And this gradient is going to go from green to red. You can manipulate it as you like. We'll plug in these values and use these as the S input for color. And now we can see red is representing our sort of very far locations, and green is representing those ones that are very close to a subway entrance. So we might want to turn our boundary surfaces back on so we can sort of understand this in context. You could play with all kinds of other custom preview mechanisms in order to visualize this the way you'd like. But that's another way to start to visualize a sort of softer condition as a field using contours. So this topic could go a lot deeper and further. We could talk about all kinds of things, but I'm going to stop here and get ready for the next tutorial, which will be about retrieving additional data sources from the web.